So in this video, I wanted to go over a homework problem that was somewhat commonly missed on the Chapter 3, Part 2 homework. We have a suitcase. It's acted upon by a set of forces, and I believe the confusion may have been related to how the questions were worded with respect to what they were asking for. Remember in Chapter 3 that we're talking about equivalent force couple systems, and that is to say that for any set of forces and couples acting upon any rigid body just meaning that the lines of actions of the forces aren't concurrent, so we have to consider their physical dimensions, and that corresponds to considering their points of application on the rigid body, that we can describe a single force applied at any point along with a couple that would tend to induce the same translation and rotation. So these set of forces are going to tend to induce a certain amount of translation and rotation of this rigid body. If we wanted to create an equivalent effect by a single force applied at a point and a couple, we know how to do that. The way that we do that is we just find the resultant force at any point that we wish to determine the equivalent force couple system by just adding up all the forces. And then to find the couple that would be needed at that point, we compute the moment of all these forces about that point. So question one was pretty easy. They just said, hey, what is the resultant force? And clearly you know that they're talking about some kind of equivalent force couple system. But even if you don't, as long as you took the first week of the class, you remember that the resultant force is nothing more than the sum of all forces acting on a body. So the only challenging thing here might have been to determine how to decompose this 212 Newton force into X and Y components. How you wanted to do it is look at the line of action and notice that it naturally forms a right triangle with respect to the dimensions of the suitcase, which has a base of 450 and a height of 280. So that would allow us to determine this angle theta directly by taking the inverse tangent of 280 divided by 450. However, since in order to do the force decomposition, we're not going to need theta, we need cos theta and sine theta, probably easier just to form a right triangle, compute the length of the hypotenuse, and get that the cosine of theta is equal to 450 divided by whatever that side length is. I got about 0.8491, and similar thing for the sine of theta. Just noting, of course, that we're talking about this angle, so the opposite side length is 280. When you actually do your decomposition, don't forget that this force is directed in positive x and negative y, and if you're not describing this angle as negative, you need to do a manual adjustment and add your negative on into there. Once you have these into rectangular components, it's very easy to add all the forces together because each of the other three forces are purely in the x or y direction. So what do they mean about part two? And I want to go just kind of read the actual way it was worded just to kind of at least explain to you why I thought it was confusing. They say, locate the 2 points where the line of action of the resultant intersects the edge of the suitcase. Well, remember for this problem that we're working on here, we can determine an equivalent force couple system at any point. And generally speaking, the couple will be non-zero. However, there's only a finite set of points where the resulting couple would be zero. And what that means is that any point along what we're going to find that set of points as a line, it's going to feel like it's purely being translated. It's not going to experience any rotation. So what we want to do is basically determine the force couple system about some point on the edge of this suitcase. The way that I did it is I picked this upper right-hand point, which is B, and then we're going to ask ourselves, can we find another point on the suitcase such that the resulting force couple system would have zero couple? So let's begin by computing the force couple system about point B. All that we need to do is compute the moment of each of these forces about that point. The nice thing about this is clearly vector P will not have a moment about point B because its line of action passes through, and the x component of the 212 Newton force will not have a moment about point B because its line of action passes through as well. So I only need to consider three individual forces with respect to computing the moment about point B, which is the couple in our equivalent force couple system, namely this 180 Newton force. If you pin your paper at point B and rotate it in that direction, you notice that this 180 Newton force induces a clockwise rotation, so it will be negative. The 100 Newton force is going to induce a counterclockwise rotation, and in a similar fashion, again, the way you get that is imagine pinning the suitcase at B, pushing it in that direction, and notice you're going to get a counterclockwise rotation. And the vertical component of this force is also going to introduce a counterclockwise rotation. All you need are your perpendicular distances for this vertical component, 450 millimeters or 0.45 meters for this 100 Newton force. Notice that the line of action, which is a horizontal line, is 0.1 meters separated from point B. And same idea for the 180 Newton force, it is 0.28 meters away. So if you just sum all those together, being careful with your sign convention, counterclockwise positive convention means that, again, the 180 Newton force is going to be inducing a negative moment and the other two are positive. You can find the equivalent couple of the force couple system about B. Now what you want to ask yourself is, well, how could I find another point, and remember, it's really going to be an entire set of points corresponding to the line of action, where the couple of the equivalent force couple system is zero. So what we want to ask ourselves is, if we went from the edge of the suitcase at point B and we moved the actual resultant force from being applied at point B to some other point along that top edge of the suitcase, at what separation x would the resulting moment that we're computing be equivalent to the couple of the force couple system at B? So it's really, really confusing. It's kind of hard to wrap your head around, but the idea is that all those forces effectively at point B induce a resultant force of this much and a couple of this much. So what we're asking ourselves is, can we find another point on the suitcase such that obviously the resultant force is not going to change, but that basically the couple will turn out to be equivalent to that value that we just determined. And then I should have reworded that a little bit. Remember, when we're finding a force couple system about any point, like if we're finding the force couple system about some point that's x units away from B, the way that we do that is we compute the actual moment of the force about point B. And in this case, we just want that to be equivalent to the actual couple that we computed above. And big idea is that if once we find this point, remember that force is going to have a line of action, and any point along that line of action is going to have the actual same couple. So when you're trying to find the point of intersection on the actual vertical axis, you could do it the same way that we did. Of course, you're only going to use the x component of the actual resultant force, because the y component of the resultant force, if it's any point along this edge, would have a line of action through B. Or you can just use the fact that we know, again, that if the resultant force is kind of intersecting the top edge at this point, that we can use an equivalent triangle, since we know the x component and the y component of the resultant, in order to determine what that y distance is, namely y divided by x. Y is what we want to know. We know that x is whatever value you determine from above, and you can set that equal and solve using this approach.